Hello, our research topic is class imbalance in deep learning. This is the outline of the presentation. First, I'll give introduction to class imbalance. Then I'll give overview of some of the strategies used in deep learning to address class imbalance. Then I'll show some experimental results using those strategies. First, introduction to class imbalance. Class imbalance arises in a dataset when number of samples belonging to a class is significantly lower than those belonging to other classes. As a result, model gets biased towards the majority class and it leads to poor performance on the minority class. Often critical applications which require a rare event prediction suffer from class imbalance problem. Two real world examples of class imbalance problem are shown on the screen. First is in the case of image classification where the number of images in a particular class is significantly lower than the number of images in other class. And another is in the case of semantic segmentation where the number of pixels belonging to a particular class in image is significantly lower than the number of pixels belonging to other classes. For example, the number of pixels for pedestrian class in this image. Then these are some of the challenges which are encountered when dealing with imbalanced datasets. First is overfitting to minority class, since the number of images in the minority class are less. It leads to overfitting on the minority class. Then evaluation metrics like accuracy are misleading in the case of imbalanced dataset, because even if the model predicts majority class on all the data points, it still leads to a higher accuracy. As a result, misleading accuracy is misleading. Therefore, we'll need alternative evaluation metrics like recall and precision. Then often sensitive applications like cancer prediction suffer from imbalanced datasets because their recall is more important. And to address class imbalance, mostly the resampling techniques are used in deep learning, which involve resampling of data or creation of new data, which introduce complexity in data pre-processing. Then, since the model is biased towards the majority class, it's because of dominated loss gradients of majority class. Then I conducted few experiments on one imbalanced dataset, whose description is shown on the screen. It is a oral cancer screening dataset received by Biocon Foundation. It has total 29573 images, of which 4887 images belong to minority class and 24686 images belong to majority class. Some examples of images from the dataset are shown on the screen. I conducted these experiments on mobile VIT V2 model. I trained this model for 50 POCs with a batch size of 64 with Adam optimizer. Then overview of some of the strategies to address class imbalance in deep learning. Mainly, there are three strategies that are used. First is pre-processing technique. They modify the training data to balance number of samples across classes. Sample includes oversampling minority class. Second is post-processing technique. It adjusts model predictions after training. Example is changing decision threshold after training. And third is learning stage algorithm. They modify the training process to address class imbalance. Its example includes modifying the loss functions. Then in pre-processing techniques, first is undersampling the majority class. Since majority class is undersampled, it leads to a smaller dataset, which can reduce the training time, but it may discard valuable data points from the majority class. Example includes random undersampling and cluster-based undersampling. On the considered dataset, whose description I shown you previously, with baseline that is just using cross entropy loss, I got sensitivity of 75.48 and specificity of 90.45. And with random undersampling, I got sensitivity of 83.63 and specificity of 85.17. These results are reported by conducting the same experiment 10 times, and the mean and standard deviation of results are reported. So These are these are some. This is about random oversampling. It preserves all available data, but it may lead to overfitting of minority class due to repeated samples. The increased dataset size results in longer training times. The examples include random oversampling, the minority class, and synthetic minority oversampling technique. With the random oversampling of minority class, I got sensitivity of 76.21 and specificity of 90.10, which is almost similar to baseline. So I didn't get improvement over the considered dataset using random oversampling. Then this is about the post-processing techniques. It can be applied without changing the training process. It leads to a trade-off between sensitivity and specificity. It allows more samples to be classified as the minority class. It, examples include using validation data to determine optimal threshold and thresholding based on prior class probabilities. So on one model, I plotted a ROC curve and used the geometric mean of sensitivity and specificity to come up with an optimal threshold. The results you can see on the screen. Then the learning stage algorithms. They modify the training process to address class imbalance. They require no changes to the original dataset as required in pre-processing techniques. Its examples include modifying loss functions, which I'll describe next in this presentation. Other examples are curriculum learning, introduces, which gradually introduces harder examples. Another example is transfer learning, which uses pre-trained model on a balanced dataset before fine-tuning on the imbalanced dataset. And another example is two-stage learning, where the representation learning and classifier learning is separated out. Then, before discussing other modified loss functions for class imbalance, let's see what problem is in cross entropy loss. So, if we take the Taylor series expansion of cross entropy loss, we'll get this equation. So, and if we take its negative gradient as required in gradient descent, then we'll get this. So, as you can see here, we'll get sorry, we'll get one as a constant, and this is just for one example. So, for as many number of examples in majority class, we'll have that number here. So, as a result, we can say that the model is loss gradient is biased towards the majority class. And the results with the baseline cross entropy loss on the considered data, which I have shown previously, is 75% sensitivity and 90% specificity. The first loss to address class imbalance is weighted cross entropy loss. The equation is shown on the screen. It assigns different weights to each class. Setting higher weights for minority class helps the model to focus more on learning from minority samples. So using weighted cross entropy loss, I got sensitivity of 83.79 and specificity of 85.71, so which is a good improvement over the baseline results. Then focal loss, this is whose formula is given here. It reduces the loss contribution of well-classified samples. Uh, Sensitivity and specificity results are shown here. With using focal loss also, I got a good improvement over baseline results. The main difference between focal loss and weighted cross entropy loss is focal loss allows to assign different weights to same examples within the class. Then this is a polynomial polyloss, which is recently proposed in 2022 in ICLR paper. It allows to modify the standard cross entropy loss via Taylor expansion. It allows the importance of different polynomial bases to be adjusted. We can see that by choosing appropriate epsilon I, we can cross entropy focal loss and weighted cross entropy loss is a special case of polyloss. For example, putting epsilon I equal to 0 for all I will give us cross entropy loss. So how does polynomial loss address helps in addressing class imbalance? See, if as I've shown previously, the negative of loss gradient of cross entropy loss is shown here. So by choosing only one loss, that is, we will consider only the first term here for epsilon 1, and of all other terms at 0, we'll get this equation. And if we put just the epsilon 1 equal to -1 in this term, then we will remove the leading polynomial term in the cross entropy loss. And as a result, we can get rid of this constant from the cross entropy loss. So this is how it can help in reducing class imbalance. Then how we can see the weighted cross entropy loss in a special case of polynomial loss? Just by setting epsilon I equal to this W divided by WT minus 1 divided by epsilon I, where W is number of samples in training set and WT is the number of samples in 2 class T, you can get weighted cross entropy loss. Similarly, for focal loss, we can use epsilon I equal to WT1 minus VT raised to gamma minus 1 divided by epsilon I. So in the paper, there is one figure in the polynomial loss paper. There is this figure. The focal loss only allows the horizontal adjustment if we don't consider omega t, but poly loss allows the vertical adjustment as well. Then the authors of poly loss paper have shown that poly 1 loss with epsilon greater than 0 leads to a better performance than the cross entropy loss on ImageNet 21K dataset. This could be because they were able to analyze more by using epsilon positive to harder examples. They got about improvement over baseline cross entropy loss by about 0.4 or 0.5% increment. And they explain that and this is because the model confidence has increased by using positive epsilon. They show it in this figure. You can see that with a positive epsilon that is equal to 1, the prediction confidence has increased over the cross entropy loss. So that's the reason for some improvement over the ImageNet 21K dataset. Then these are the experimental results. These I have shown you previously, but again, to summarize, with baseline, I got sensitivity of 75.48 and the specificity of 90.45. With random undersampling and weighted cross entropy loss, somewhat similar results are obtained, which are a huge improvement over the baseline. Then focal loss also helped, and only the random undersampling did not help that much on the considered dataset. And then we also tested as since the authors in poly loss paper have got improvement by using positive epsilon. We also used positive epsilon and tried to compare with other methods, but we did not see any improvement in the min confidence of the prediction by using poly loss, as you can see on the graph for both class 0 and class 1. In fact, for class 1, the min confidence has decreased a little bit in the initial epochs, but as such, we don't see any improvement over min confidence by using polynomial loss. The further investigation is required with what the impact of using positive epsilon in poly 1 loss. So these are the references that I have used. Thank you.